Hello friends, you're on the Quesaria channel, and today we're diving into one of the most unexpected mysteries of the cosmos. Imagine a cloud of alcohol stretching 463 billion kilometers. This isn't science fiction, it's reality existing right in the center of our Milky Way. This giant cloud of ethyl alcohol, the same kind found in alcoholic beverages on Earth, is located near the center of our galaxy, approximately 26,000 light-years away. To understand the scale, if we could travel at the speed of light, it would take nearly 6 years to fly from one edge to the other. This celestial brewery is located in a region astronomers call Sagittarius B2. It's one of the largest molecular clouds in our galaxy, a true factory for producing complex organic molecules. The temperature there is around minus 173 degrees Celsius, and in these extreme conditions, amazing chemical processes occur. But how did alcohol end up in space? This question puzzled scientists for a long time. It turns out the cosmos is a massive chemical laboratory. In interstellar space, atoms of hydrogen, carbon, and oxygen, the most abundant elements in the universe, meet on the surface of tiny dust particles. These particles act as catalysts, helping atoms bond into more complex molecules. The formation process begins with simple molecules. First, formaldehyde forms, then methanol, and through a series of chemical reactions that can take millions of years, ethanol is born. Interestingly, alongside ethanol, about 50 different organic compounds have been found in this cloud, including formic acid, acetone, and even glycolaldehyde, the simplest sugar. The quantity in the Sagittarius B2 cloud is staggering. According to astronomers' calculations, it contains approximately 10 to 28 liters of ethanol. This number is so vast it's hard to comprehend. If every person on Earth drank half a liter of this celestial brew daily, it would last for quadrillions of years, a period millions of times longer than the age of the universe itself. Of course, this celestial cocktail isn't suitable for consumption. First, the concentration is extremely low, about 1 molecule per cubic centimeter. That's less than 1 drop in an Olympic-sized pool. Second, the cloud contains many other, often toxic substances, such as hydrogen cyanide, ammonia, and methanol, which is deadly to humans. The discovery wasn't accidental. In the 1970s, astronomers began using radio telescopes to study molecular clouds. Each molecule emits radio waves at specific frequencies, creating a unique fingerprint. When scientists pointed their telescopes at Sagittarius B2, they were shocked to detect the characteristic signals of ethanol. This discovery revolutionized our understanding of cosmic chemistry. Previously, it was believed that complex organic molecules could only form in Earth-like conditions. But it turned out that space is far more chemically active than we thought. The extreme cold prevailing in interstellar space actually helps preserve molecules that would instantly break down on Earth. Interestingly, Sagittarius B2 isn't the only place where ethanol has been found. It's been detected in comets, around young stars, and even in gas clouds surrounding some galaxies. Comet Lovejoy, which passed Earth in 2015, was releasing the equivalent of about 500 bottles of wine per second into space. Of course, this is a figurative comparison, but it helps visualize the scale of the phenomenon. The presence of complex organic molecules in the cosmos has profound implications for understanding the origin of life. Some scientists believe that organic compounds, including alcohols and amino acids, could have reached Earth from space through meteorites and comets. This theory, known as panspermia, suggests that the building blocks of life are widespread throughout the universe. In Sagittarius B2, molecules directly related to biology have also been found. For example, glycolaldehyde, a simple sugar that's a precursor to ribose, a component of RNA. The amino acid glycine, one of the main building blocks of proteins, has also been detected. These discoveries confirm that the chemical prerequisites for life exist in space. Temperature conditions in these clouds are also unique. At around -173 degrees Celsius, molecules move very slowly. This allows them to stick to each other on the surface of dust particles, forming thin, icy shells. In these icy mantles, chemical reactions occur that are impossible under other conditions. When these icy particles are irradiated by ultraviolet radiation from neighboring stars or by cosmic rays, complex photochemical processes begin. The radiation energy breaks some chemical bonds and creates others, generating increasingly complex molecules. It's like a natural chemical reactor operating on scales that are hard to imagine. Research also helps astronomers better understand star formation processes. Molecular clouds like Sagittarius B2 are cradles of new stars. When part of a cloud begins to compress under its own gravity, the temperature rises, and complex molecules begin to evaporate from the surface of dust particles. By studying the composition of these molecules, scientists can trace the evolution of star-forming regions. One of the most intriguing questions is whether these molecules might play a role in forming planetary systems. When a protoplanetary disk forms around a young star, organic molecules from the surrounding cloud can become part of its composition. Later, these molecules may end up on the surfaces of forming planets. Thus, ethanol and other organic compounds could be built into planets from the very beginning of their existence. Spectroscopic studies show that complex esters are also present. For example, ethyl formate, a compound that on Earth is responsible for the smell of rum and raspberries. Methyl formate, another ester, has a plum scent. If we could gather all these molecules together in sufficient concentration, space would smell like a fruit cocktail. The study also has practical significance for future space missions. Understanding how organic molecules form and survive in space will help in developing life support systems for long-duration journeys. Perhaps in the future, we'll learn to use cosmic chemistry to produce necessary substances directly in space. Technologies developed for detecting molecules in the cosmos find applications on Earth as well. Spectroscopy methods refined for studying interstellar clouds are now used in medicine for diagnosing diseases, in the food industry for quality control, and even in forensics. Interestingly, the concentration of different molecules can tell us about the history of these regions. For example, the ratio of methanol to ethanol can indicate the age of the cloud and the intensity of star formation within it. It's like cosmic archaeology, where molecules are artifacts telling the story of galactic evolution. Research also shows that these compounds may play a role in forming more complex biological molecules. In laboratory experiments simulating conditions in space, scientists were able to obtain amino acids and even simple peptides starting with mixtures containing alcohols. This confirms that the path from simple organic molecules to life may begin in the cosmos. Sagittarius B2 also contains molecules used by living organisms on Earth. For instance, acetone has been found, a substance our bodies produce when breaking down fats. Propionaldehyde has also been detected, a compound used in the metabolism of some bacteria. These discoveries blur the line between cosmic chemistry and biochemistry. This research also aids in the search for extraterrestrial life. If complex organic molecules are widespread in space, it increases the probability that life could arise elsewhere in the universe. Next-generation telescopes like the James Webb Space Telescope allow us to detect organic molecules in exoplanet atmospheres, which could be a sign of biological activity. It's important to understand that these molecular clouds are dynamic systems. They constantly evolve under the influence of radiation from neighboring stars, shock waves from supernovae, and gravitational perturbations. Molecules within them are continuously forming and breaking down, creating a complex chemical cycle that lasts millions of years. One of the most mysterious aspects is chirality. On Earth, many organic molecules exist in two mirror forms, left and right. Life on our planet uses only one form of amino acids, left, and sugars, right. Scientists are trying to determine whether molecules in space have the same asymmetry, and whether this could be related to the origin of life. Research shows that in some regions, organic molecules can be partially polarized by circularly polarized light from nearby stars. This could lead to the preferential formation of one chiral form over another. If so, the cosmos may choose molecular orientation even before these molecules reach planets. These compounds also play a role in cooling interstellar clouds. Molecules of ethanol and other organic compounds emit energy in the form of infrared radiation, helping clouds lose heat. This cooling is necessary for clouds to compress under gravity and form new stars. Interestingly, some molecules form as a result of processes that on Earth require high temperatures and pressures. In space, thanks to cosmic rays and ultraviolet radiation, these reactions can occur even at extremely low temperatures. This shows that the universe has its own unique pathways of chemical synthesis. The discovery of large quantities of organic molecules has also changed our understanding of comets. Previously, comets were thought to be simply dirty snowballs of water and dust. Now we know they contain a complex set of organic compounds, including alcohols. When comets approach the sun, these molecules evaporate, creating characteristic tails. The European Space Agency's Rosetta mission, which studied Comet Churyumov-Gerasimenko, found glycine and phosphorus on its surface, key components of DNA. Methyl and ethyl alcohol were also found. This confirms that comets could have been cosmic couriers delivering organic molecules to early Earth. This research also helps us understand galactic evolution. The quantity and distribution of organic molecules in a galaxy can reveal its history of star formation, how many generations of stars have already existed, and which processes dominated its evolution. It's like a chemical signature unique to each galaxy that in some galaxies, particularly high concentrations of methanol, a simpler relative of ethanol, have been detected. These methanol masers emit powerful radio emissions at specific frequencies. Astronomers use them as beacons to study galactic structure and dynamics. This shows how these molecules become tools for exploring the universe. It's important to note that this phenomenon isn't just a curiosity. Its study helps answer fundamental questions about our place in the universe. If organic molecules are widespread in space and can form naturally in interstellar regions, then life may not be a unique terrestrial phenomenon, but a natural consequence of cosmic evolution. Research also shows that even more complex molecules can form in these clouds than previously thought. Recently, polycyclic aromatic hydrocarbons, complex ring structures that could be precursors to more sophisticated biological molecules, were detected in the TMC-1 cloud. This expands our understanding of cosmic chemical complexity. The temperature gradient in these clouds creates unique conditions for chemical reactions. In the coldest regions, molecules are frozen on dust particle surfaces. In warmer areas, they evaporate and engage in gas phase reactions. This freeze-evaporation cycle can last millions of years, creating increasingly complex molecules. Interestingly, some astronomers suggest the existence of cosmic oases, regions in interstellar space where organic molecule concentrations are particularly high. These areas could be ideal places for primitive life forms to emerge, or at least for prebiotic molecules to form. Searching for such oases is one of modern astrobiology's tasks. This research also has philosophical significance. It shows that the universe isn't a cold, dead desert. On the contrary, it's a dynamic system where chemical processes constantly occur, generating complexity. From simple hydrogen atoms to complex organic molecules, the cosmos demonstrates a tendency toward increasing complexity and matter organization. Detection technologies continue to improve. New radio telescopes like ALMA in Chile allow detection of increasingly weak signals from increasingly rare molecules. This opens new horizons for understanding cosmic chemistry. Each new discovery adds details to the overall picture of the universe's chemical evolution. It's also important to understand the role these compounds play in the energy balance of the interstellar medium. Molecules of ethanol and other organic compounds absorb and re-emit energy at specific wavelengths. This affects how energy from stars spreads through the galaxy and how quickly gas clouds can cool and compress. Some scientists suggest that these molecules may have played a role in the emergence of the first organic molecules on Earth. If our planet was bombarded by comets and meteorites rich in organics, these molecules could have become the seeds for further chemical evolution. Experiments show that organic molecules can survive meteorite impacts and even form more complex compounds. Interestingly, concentrations can vary greatly in different parts of molecular clouds. In some hot spots, it may be thousands of times higher than the cloud average. These regions are often associated with young stars or areas where active chemical processes occur. Studying such hotspots helps understand the mechanisms of organic molecule formation. These compounds also play a role in forming ice on dust particle surfaces. Ethanol molecules can become incorporated into water ice's crystalline structure, changing its properties. This drunken ice may have different melting temperatures and other physical characteristics, affecting processes in protoplanetary disks. Research shows that some clouds contain not only simple alcohols, but also more complex ones like propanol and butanol. This indicates that cosmic chemical complexity may be much higher than previously thought. Each new discovery expands our understanding of cosmic chemistry's possibilities. It's also important to note that these molecules can be indicators of other, not yet detected molecules. If ethanol is present in a certain area, other organic compounds are likely there too. This helps astronomers plan observations and search for new molecules in space. This research also has significance for understanding exoplanet atmospheric chemistry. If organic molecules can form in interstellar space, they may be present in planetary atmospheres. Detecting such molecules could indicate a planet's habitability or even evidence of biological activity. These clouds also contain isotopes, atoms with different numbers of neutrons. The ratio of different isotopes can reveal the cloud's temperature and density, as well as the processes occurring within it. This is an additional tool for studying physical conditions in interstellar space. Interestingly, some molecules in these clouds have properties that make them potentially useful for future technologies. For example, certain organic molecules could be used as components for producing fuel or plastics in space. This opens prospects for utilizing cosmic resources in future missions. The research also helps understand processes in nebulae, remnants of supernova explosions. In these extreme environments, organic molecules can be destroyed and reformed, creating a unique chemical cocktail. Studying these processes helps understand how chemical elements circulate through galaxies. It's important to note that this isn't a static phenomenon. Molecules are constantly forming, breaking down, freezing, and evaporating. This dynamic process continues for billions of years and is part of the great cosmic cycle of matter and energy. Some scientists suggest that these compounds may influence magnetic field formation in interstellar space. Molecules with dipole moments, like ethanol, can align along magnetic field lines, affecting the polarization of light passing through the cloud. This allows astronomers to map magnetic fields in galaxies. The discovery has also stimulated new theories about the origin of life. The metabolism first theory suggests that life began with simple chemical cycles that could have included alcohols and other organic molecules. If such molecules are widespread in space, this supports the idea that life can arise naturally wherever suitable conditions exist. This research also aids in calibrating astronomical instruments. Since ethanol spectral lines are well known, they can be used as standards for tuning spectrometers. This increases the accuracy of astronomical observations and helps detect other, less common molecules. Interestingly, some clouds contain molecules used as flavorings on Earth. Besides the already mentioned ethyl formate, rum smell, and methyl formate, plum smell, dimethyl ether, ethereal smell, and acetaldehyde, fruity smell, have been found. If we could gather all these molecules together, space would have quite a pleasant aroma. Research also shows that these molecules may be linked to water in space. In many clouds, ethanol and water vapor are present together, and their ratio can indicate physical processes occurring in the cloud. This helps astronomers understand how water, a key molecule for life, is distributed in space. It's important to understand that studying these compounds is part of a larger picture of investigating the universe's organic chemistry. Each new discovery adds a piece to the puzzle, helping us understand how complexity emerges from simple atoms and how this complexity might ultimately lead to the emergence of life. These clouds may also contain precursors of nucleotides, the building blocks of DNA and RNA. Although nucleotides themselves haven't been detected in space yet, many of their components have been found, including nitrogenous bases and sugars. This confirms that the chemical prerequisites for the genetic code can form in space. Technologies developed for studying these molecules find applications in many terrestrial fields. Remote molecular detection methods are used for monitoring atmospheric pollution, searching for minerals, and even diagnosing diseases through patient breath analysis. This research also has cultural significance. It shows that humanity isn't isolated in the universe. We're part of a grand cosmic process. The molecules we're made of are born in stars and interstellar space. We're literally made of stardust, and these organic compounds are one of the links connecting us to the cosmos. Research continues, and each year brings new discoveries. Telescopes are becoming more powerful, analytical methods more precise. Perhaps soon we'll find even more complex organic molecules in space, maybe even precursors of proteins or nucleic acids. Each such discovery brings us closer to understanding how life arose and how widespread it might be in the universe. These compounds also play a role in forming comets and asteroids. When a protoplanetary disk cools, organic molecules can condense on dust particle surfaces, which then stick together, forming larger bodies. Thus, alcohols and other organic compounds can be frozen into comets from the moment of their formation. Interestingly, this research also helps understand stellar aging processes. When stars approach the end of their lives, they eject enormous quantities of dust and gas enriched with heavy elements into space. Organic molecules, including alcohols, can form in these ejecta. Thus, one star's death can become the beginning of chemical evolution in another part of the galaxy. Research shows that in some cases, these molecules can form very quickly, within a few thousand years after dust particle formation. This is much faster than previously thought and indicates the high efficiency of cosmic chemistry. Nature has found ways to create complex molecules even in the extreme conditions of space. It's also important to note that these compounds can be indicators of future star formation. Regions with high organic molecule concentrations are often places where new stars will soon begin forming. This allows astronomers to predict where the next burst of star formation will occur in a galaxy. This research also helps understand dust's role in space. Dust particles aren't just passive participants. They're active catalysts for chemical reactions. Their surfaces provide places where atoms and molecules can meet and react. Without dust, many organic molecules simply couldn't form. Some scientists suggest that these molecules may even influence galactic evolution. The cooling provided by organic molecules can affect star formation rates, which in turn influences a galaxy's chemical composition and structure. This shows how even relatively simple molecules can have far-reaching cosmological consequences. It's also interesting that concentrations can change over time. In the young universe, when there were fewer heavy elements, organic molecules were much less abundant. Over time, as generations of stars enriched the cosmos with carbon, oxygen, and other elements, the quantity of organic molecules grew. We live in an era when the cosmos has reached chemical maturity. This research also has significance for searching for life on other planets. If we know which organic molecules are common in space, we can better assess which planets have the greatest potential for life to emerge. The presence of certain molecules in an exoplanet's atmosphere could indicate its habitability. It's important to note that we're talking about an entire family of alcohols, from simple methanol to complex polyatomic alcohols. Each has unique properties and may play different roles in cosmic chemistry. Together, they form a complex network of chemical reactions. This research also helps understand how molecules survive in extreme conditions. Cosmic rays, ultraviolet radiation, extreme temperatures, all this should quickly destroy organic molecules. But they survive, and understanding the mechanisms of this survival may have practical applications, from radiation protection to food preservation. These clouds are also natural laboratories for studying phase transitions. At different temperatures and pressures, molecules can transition from gas phase to solid and vice versa. These transitions affect chemical reactions and the physical properties of clouds. Studying these processes helps understand condensed matter physics. Researchers have also found that some clouds contain not only neutral alcohol molecules, but also their ionized forms. These ions can be more reactive and participate in other types of chemical reactions. This adds another level of complexity to cosmic chemistry. Interestingly, this research also helps understand processes in the upper layers of planetary atmospheres. On Titan, Saturn's moon, complex organic chemistry, including alcohols and other compounds, has been detected. Understanding how these molecules form in space helps interpret data from space missions. It's also important to note that these molecules could be energy sources for primitive life forms. On Earth, some bacteria can use methanol and ethanol as carbon and energy sources. If similar organisms exist elsewhere in the universe, these compounds could literally be their food. This research has also stimulated the development of new theoretical models of chemical evolution. Computer simulations can now predict which molecules will form under different conditions and where to look for them. This makes the search for new molecules more targeted and effective. These compounds also play a role in forming snowlines in protoplanetary disks. These are distances from a star where certain molecules transition from gas phase to solid. Ethanol's snowline differs from water's snowline, affecting the chemical composition of planets forming at different distances from a star. This research also has philosophical significance for understanding our place in the universe. If molecules necessary for life form naturally throughout the cosmos, this confirms the idea that life isn't an accident, but a natural result of cosmic evolution. We're not alone in the universe, at least on a molecular level. Research continues, and the future promises even more exciting discoveries. New space telescopes will allow detection of organic molecules in exoplanet atmospheres. Missions to comets and asteroids will bring samples of material to Earth for detailed analysis. Perhaps we'll soon learn how widespread life is in the universe. These molecules also play an unexpected role in forming stellar winds. When young stars emit powerful streams of charged particles, organic molecules in the surrounding environment can influence how these winds interact with the interstellar medium. Molecules of ethanol and other alcohols can absorb wind energy, converting it into thermal radiation, which changes the dynamics of the entire system. It's fascinating that in some regions of space, concentrations are so high that if we could somehow collect it, we'd have oceans of alcohol. Of course, this is impossible due to the vast distances and extremely low density of the interstellar medium. But the very idea of cosmic alcoholic oceans captures the imagination. Research shows that these molecules can form through different pathways. One is surface reactions on dust particles, where hydrogen atoms attach to CO molecules, first forming formaldehyde, then methanol, and finally ethanol. Another pathway is gas phase reactions, where ions and radicals react in open space. Each mechanism dominates under different conditions, creating a complex mosaic of chemical processes. Interestingly, temperatures can range from almost absolute zero to several hundred Kelvin near young stars. These temperature gradients create chemical zones where different types of reactions dominate. In cold zones, molecules accumulate on dust surfaces. In warm areas, they evaporate and react in the gas phase. Studying the isotopic composition also reveals interesting information. The deuterium to hydrogen ratio in ethanol molecules can reveal the temperature at which they formed. It's like a thermometer frozen into the molecular structure, preserving information about conditions from millions of years ago. These compounds may also be key to understanding the origin of water on Earth. Some theories suggest that water and organic molecules were delivered to our planet by comets and asteroids. By studying the chemical composition of these bodies and comparing it to molecular clouds, we can trace the path of molecules from interstellar space to Earth's oceans. It's important to note that these substances aren't distributed uniformly. They concentrate in certain regions, especially around young stars and in areas of active star formation. These hot spots of organic chemistry may be places where the most complex molecules are created, possibly even precursors to life. Research has also revealed that these molecules can form complex clusters with other molecules. For example, ethanol can form hydrogen bonds with water, creating clusters with unique properties. These clusters may be more resistant to radiation and can preserve complex chemical information longer. Interestingly, some molecules in these clouds have properties that make them potential biomarkers. If we detect certain combinations of organic molecules in an exoplanet's atmosphere, it could be a sign of biological activity. Thus, these compounds become tools for searching for life in the universe. This research also helps understand processes in accretion disks around black holes. In these extreme environments, organic molecules can form and break down at tremendous rates, creating unique chemical signatures. Detecting these signatures helps astronomers study black hole physics. It's important to understand that this isn't an isolated phenomenon. It's part of the great cosmic cycle of elements. The carbon and oxygen that make up ethanol were created in stellar cores billions of years ago. After stars died, these elements were ejected into space, where they combined to form molecules. These molecules may become part of new stars and planets, continuing the eternal cycle. This research also has practical significance for astronautics. Understanding how organic molecules behave in space helps in developing life support systems for long-duration missions. Perhaps in the future, we'll learn to synthesize necessary organic compounds directly in space, using local resources. Interestingly, these molecules can influence the optical properties of the interstellar medium. Ethanol molecules absorb and scatter light at certain wavelengths, affecting how we see distant stars and galaxies. Accounting for this effect is important for accurate astronomical measurements. This research also reveals the connection between chemistry and physics of the interstellar medium. Chemical reactions can influence temperature and pressure in clouds, which in turn affects their gravitational stability. This shows how chemistry can influence the large-scale structure of the universe. Research shows that some clouds contain not only simple alcohols, but also complex polyols. molecules with multiple hydroxyl groups. These compounds could be an intermediate link between simple alcohols and sugars, showing a possible pathway to biologically important molecules. It's important to note that these molecules can be preserved in space for millions of years. Unlike on Earth, where organic molecules quickly decompose, in the cold vacuum of space, they can exist practically forever. This makes the cosmos a kind of archive of the universe's chemical evolution. Interestingly, this research also helps understand processes in the intergalactic medium. Although organic molecule concentrations there are much lower, they're still present and can influence galactic evolution and the formation of large-scale structure. This research has also stimulated the development of new molecular detection methods. Techniques developed for detecting weak ethanol signals in distant galaxies are now used in medicine for early disease diagnosis through molecular marker analysis. These compounds also play a role in forming polar caps on planets and moons. On Mars, for example, seasonal polar caps contain not only water ice and dry ice, CO2, but also traces of organic molecules, including methanol. This could have significance for future Martian colonies. It's important to understand that these molecules may be evidence of much more complex chemical processes. If ethanol molecules can form in space, then theoretically even more complex organic compounds can form. Each new discovery expands the boundaries of possibility in cosmic chemistry. Research shows that these compounds can influence the crystalline structure of ice in space. Ethanol molecules can become incorporated into the crystalline lattice, creating defects that affect ice's physical properties. This has significance for understanding the evolution of comets and icy moons. Interestingly, concentrations can be an indicator of the age of cosmic objects. Older clouds that have had more time for chemical evolution usually contain more complex molecules. This allows astronomers to estimate the age of different regions in a galaxy. This research also has significance for theories about multiple universes. If the laws of physics and chemistry are universal, then organic molecules should form everywhere there are appropriate elements and conditions. This supports the idea that life may be a natural consequence of physical laws. It's important to note that these molecules could be a carbon source for primordial life. On early Earth, when the atmosphere was poor in organic molecules, material delivered by comets and meteorites could have provided the necessary building blocks for life's emergence. This research also reveals the role of turbulence in the interstellar medium. Turbulent flows can mix different chemical zones, bringing together molecules that would otherwise never meet. This creates opportunities for new chemical reactions and the formation of even more complex molecules. Interestingly, some molecules in these clouds may have quantum properties that make them unique. At extremely low temperatures, molecules can exist in quantum states impossible on Earth. This opens new horizons for quantum chemistry. This research also helps understand processes in planetary nebulae, remnants of dying stars. In these objects, complex chemistry combines with intense radiation, creating unique conditions for synthesizing and destroying organic molecules. It's important to understand that these compounds may be key to understanding the origin of homochirality in biology. Life on Earth uses only left-handed amino acids and right-handed sugars. Perhaps this asymmetry was established in space, where certain processes could favor one chiral form over another. Research shows that these molecules can form complex polymeric structures on dust particle surfaces. These cosmic polymers could be precursors to more complex biological molecules. Studying their structure and properties helps understand possible pathways to life's emergence. Interestingly, these compounds can influence the electrical properties of the interstellar medium. Molecules with dipole moments can accumulate electric charge, creating local electric fields. These fields can affect the movement of charged particles and chemical reactions. This research also has significance for understanding galactic nuclei evolution. In active galactic nuclei, where conditions are extreme, organic molecules can survive in unexpected places, giving us information about physical processes in these exotic environments. It's important to note that these molecules may be part of complex chemical networks where hundreds or thousands of different reactions occur simultaneously. Modeling such networks requires powerful computers and sophisticated algorithms, but allows prediction of which molecules can form under different conditions. This research also reveals the role of metals in cosmic chemistry. Even trace amounts of iron, magnesium, or silicon can catalyze reactions leading to organic molecule formation. This shows how all elements of the periodic table work together in the great cosmic symphony. Interestingly, this research helps interpret data from the Perseverance rover and other missions. Understanding how organic molecules form and are preserved in space helps identify potential biosignatures on Mars and other planets. These compounds may also play a role in forming planets' primordial atmospheres. When a planet forms from a protoplanetary disk, organic molecules can evaporate from its surface, creating an initial atmosphere. This atmosphere's composition can determine the planet's subsequent evolution. It's important to understand that these molecules are a window into the universe's past. By studying organic molecules in distant galaxies, we see chemistry that occurred billions of years ago. This allows us to trace the evolution of cosmic chemistry from early epochs to the present. Research shows that in some regions of space, chemical clocks may exist, reactions that occur at predictable rates. By measuring ratios of different molecules, we can estimate how much time has passed since chemical evolution began in a certain region. Interestingly, these compounds may be connected to dark matter. Some theories suggest that dark matter's interaction with ordinary matter could catalyze chemical reactions. Though speculative, studying the distribution of organic molecules could provide clues about dark matter's nature. This research also has significance for understanding meteorite origins. Organic molecules found in meteorites may have formed in interstellar space before becoming part of the solar system. This makes meteorites time capsules, preserving information about ancient cosmic chemistry. It's important to note that these molecules can affect the speed of sound in the interstellar medium. Gas molecular composition determines how quickly sound waves propagate through it, affecting shockwave formation and interstellar medium dynamics. This research has also stimulated the development of astrochemistry as a separate scientific discipline. This field unites astronomy, chemistry, physics, and biology, creating an interdisciplinary approach to studying the universe. Each new discovery in astrochemistry expands our understanding of the cosmos. Interestingly, these molecules can be indicators of cosmic weather. Changes in organic molecule concentrations can indicate the passage of shock waves, supernova outbursts, or other energetic events. This allows astronomers to track dynamic processes in galaxies. This research also has philosophical significance for understanding Earth's uniqueness. If organic molecules are widespread in space, it decreases the probability that Earth is unique in its ability to support life. Perhaps life is a cosmic imperative, not a terrestrial accident. It's important to understand that these molecules may be part of matter's self-organization process in the universe. From simple atoms to complex molecules, from molecules to life, the cosmos demonstrates a tendency toward increasing complexity. Alcohols and other organic molecules are rungs on this ladder of complexity. Research shows that these compounds can influence the magnetohydrodynamics of the interstellar medium. Ionized molecules can interact with magnetic fields, affecting their structure and evolution. This adds another level of complexity to interstellar space physics. Interestingly, this research may help in terraforming other planets. Understanding how organic molecules form and survive in extreme conditions could help create artificial biospheres on Mars or other planets. These compounds are also subjects of science fiction and popular culture. The idea of giant clouds of alcohol in space captures the imagination of writers and artists, creating bridges between science and art. This helps popularize astronomy and attract new people to studying space. It's important to note that this research continues, and each year brings new discoveries. Telescopes are becoming more powerful, analytical methods more precise. Perhaps soon we'll find even more complex organic molecules that will change our understanding of cosmic chemistry and life's origins. Studying these compounds is a journey into the depths of space and time that reveals fundamental processes shaping the universe. From simple atoms to complex molecules, from chemistry to life. These compounds are part of the great cosmic story in which we all are participants. Friends, our journey into the world of these molecules shows how amazing and complex the universe is. A cloud of ethanol stretching 463 billion kilometers isn't just an interesting fact. It's a window into understanding how the cosmos creates complexity from simplicity, how the building blocks of life are born, and how we as humans are connected to the great cosmic dance of molecules and stars. So, friends, we've taken an incredible journey through cosmic spaces where giant clouds reveal the universe's secrets to us. This celestial brewery in the heart of our galaxy is much more than just a curiosity for news headlines. It's proof that the cosmos is a living, dynamic, chemically active space where molecules that could become the basis of life are born every second. Think about this for a moment. Somewhere out there, 26,000 light years away from us, in the cold darkness of space, atoms of hydrogen, carbon, and oxygen, the same atoms that make up you and me, are dancing their cosmic dance, forming ethanol molecules. These molecules can exist for millions of years, travel through the galaxy, become part of new stars and planets, and perhaps someday become part of a living being on some distant world. Each discovery in this field reminds us that we're not separate from the cosmos. We are part of it. The carbon in our DNA, the calcium in our bones, the iron in our blood, all of this was forged in the hearts of stars billions of years ago. And now we know that even complex organic molecules, similar to those in our bodies, form naturally in molecular clouds. This knowledge changes our perspective on the question, are we alone in the universe? If the building blocks of life are scattered throughout space, if the chemistry of life isn't a terrestrial anomaly, but a cosmic norm, then perhaps somewhere out there in another corner of this or another galaxy, other beings are also looking at the stars and asking the same questions we are. Studying these compounds is also a reminder of how young our science is. 100 years ago, we didn't know about the existence of other galaxies. 50 years ago, we didn't suspect that space was filled with organic molecules. What will we learn in the next 50 years? What secrets will the universe reveal to us? Perhaps the most important lesson we could draw from this story is one of humility and wonder. Humility before the majesty and complexity of the universe, which turns out to be far richer and more amazing than we could have imagined. And wonder that we, small beings on a small planet, were able to solve these cosmic mysteries by looking at the stars through our telescopes and analyzing light that has traveled to us for thousands of years. Next time you look at the night sky, remember the huge cloud of ethyl alcohol in the center of our galaxy. Remember that there, in the darkness between the stars, an incredible chemical symphony is taking place, where molecules are born that could become the basis of life. Remember that you're not looking at empty space, but at a vast cosmic laboratory where the universe experiments with matter and energy, creating increasingly complex forms. And who knows? Perhaps someday humanity will learn to use these cosmic resources. Perhaps future generations will travel between stars, using these compounds as fuel or raw materials for synthesizing necessary substances. Perhaps we'll learn to read the chemical signatures of distant worlds as easily as we read books today. But even if this doesn't happen, the very knowledge of this phenomenon's existence enriches our understanding of the universe. It shows that the cosmos isn't a cold, dead desert, but a living, dynamic system full of surprises and wonders. It reminds us that science isn't dry facts and formulas, but an exciting adventure, a journey into the unknown, where each discovery generates new questions. So let's continue looking at the stars with wonder and curiosity. Let's continue asking questions and seeking answers. Because who knows what other amazing secrets the universe is hiding from us? What other incredible discoveries await us beyond the cosmic horizon? Thank you, friends, for being with us on this exciting journey. This was the Quasarea channel, where we reveal the most amazing secrets of the cosmos. Subscribe to the channel so you don't miss new discoveries, like if you enjoyed it, and share this video with friends. Let them also learn about the incredible cloud stretching 463 billion kilometers. Remember, each of us is made of stardust, and perhaps even from molecules that were once part of that same cloud. We are all children of the cosmos, and the cosmos continues to amaze us with its wonders. Until we meet again on the Quasarea channel, where the universe reveals its deepest secrets.